the real solution to the nuclear magic number shells was come to when people realized that the spin-orbit interaction played a large part to the nuclear energy levels, much larger than the similar thing in the atomic levels. And this was the work of Maria Geppert-Mayer in the United States and another group in Germany. Maria Geppert-Mayer won the Nobel Prize for this work, being the second woman to do so after Marie Curie, who we met earlier in the course. So the idea is that when you're writing the potential that a proton or neutron feels, you have to do more than just write a radially symmetric potential like the square well or the isotropic oscillator. You have to add to that some thing based on the spin and the orbit interacting. So in this function, there's a radial weight factor for this thing, but as a proton or neutron has a particular orbital angular momentum that interacts with that same proton or neutron's spin, and it's the direction and alignment of those matters. So if the spin is up and the orbit is counterclockwise, or L's is up, then you have a subtraction from the potential, and if it's up, down, then you have an addition to the potential. In the atom, there's the same effect. The electron sees the charge of the nucleus spinning around it in its own rest frame, if it has an orbital angular momentum, and that loop of the nucleus around the electron gives rise to a magnetic field, and the spin of the electron aligned with that magnetic field or not, or anti-aligned, gives rise to a change in the energy that gives the fine structure of atomic spectra. And it's in that aspect that the parameter alpha was first introduced as the fine structure constant. Turns out that in nuclear physics, this effect is much larger relative to the potentials. So to go through some of the adding and subtracting of angular momenta, we have a total angular momentum J that comes from both the orbital angular momentum of the nucleon and its spin, and that's a vector equation, and we can square it. So J squared then will be L squared plus S squared plus 2 times L dot S, and it's for that reason that we want to look at J squared, because we need this L dot S term. If we then look at the average value of L dot S, averaged in the quantum mechanical sense of taking the expectation value, that will be the average of 1/2 of J squared minus L squared minus S squared. And we know how to calculate that in quantum mechanics. That's h bar squared over 2 times J plus 1 minus L plus 1 minus S plus 1. S plus 1, since S is a half, is always 3/4. And when we do the whole calculation, we find that this is h bar squared over 2 times either L, when J equals L plus 1/2, or minus L plus 1 when J equals L minus 1/2. So when we then calculate the change in the energy level, we have to do an integration over the wave function. So if we do it in the case where j equals L plus a half, we get a term that looks something like h bar squared L over 2, and then we're doing the integral over d cubed r over all space of the wave function psi n L squared times this f of r factor that we introduced. We can write a similar when j equals L minus a half, and we get an h bar squared L plus 1 over 2 times the same integral. Then and I forgot to put the minus sign in that one. So the total change in energy then is going to be something like h bar squared L plus a half times the integral of d cubed r psi n L squared f of r. The important thing to note here is that the energy, the splitting caused by the spin-orbit interaction depends on this integral, but grows with growing L. And so what happens is that each one of the states we had that had a finite L, some orbital angular momentum, gets split into two states. So that the first state, the 1s state, doesn't change. The 1p state gets split into 1p 1/2 is a higher energy, 1p 3/2 is a lower energy, but there are still 6 there, so we have 2 plus 4 plus 2 giving the 8 that we had originally. This particular version takes the square well levels, and so the 1d state gets split into 2, and such that the 1d 3/2 state goes above the 2s state, whereas the 1d 5/2 gets lowered and stays lower. And so while in the square well we had 1s, 1p, and 1d going up to 18, in this case we also add the 2s state to become 20. We go up a little further, the 1f state gets split even more, and that separates out this 1f 5/2 or 7/2 state, which has 8 in it. So we take the 20 and we add the 8 and we get 28. And then there's a cluster of the 1f high state and the 2p states and even the 1g low state to give the going up to from 28 to 50, the 32 more states that we add in that case. So when we look at all the states that we can have, there's a couple different ways to do it, and I found these from various places. This is the full table from Williams. We looked at this with the the harmonic oscillator potential. When you break it and make it more realistic, you split some of those harmonic oscillator potentials, and then the spin-orbit interaction splits the ones that have s greater than 0, that aren't s states. They get split into two parts, and you can combine them to get the magic shells with some reasonable potential here to make the splittings. This chart I found in Sakurai and Napolitano's Modern Quantum Mechanics. Here, again, they compare the harmonic oscillator, evenly spaced levels. And then you can also compare that to the infinite square well, where you have the 1 states going evenly spaced in their angular momentum splits, but the 1s, 2s, 3s, 4 going quadratically. And it reproduces this effect where the third angular momentum state of n equals 1 is just below the second n equals 2 level. That's true in both quadratic, in both the harmonic oscillator and in the infinite square well. But in either of those cases, when you make a finite well, you slightly reduce all the energy levels, and then you can round the edges too. But then you add the spin-orbit coupling, and the levels cross in just the right way to give you the magic numbers 2, 8, 20, 28. Basically, whenever there's a large gap between the energy levels, you have a completed shell. So we should then say for a given proton or neutron, we can label it based on its last completed shell. And so we can label these states as we would. So for instance, the hydrogen atom has just one proton, and that one proton we say is in a 1s 1/2 state. The deuteron has both a proton and a neutron, and they each get their own reckoning. So 1s 1/2 for the proton, 1s 1/2 for the neutron. If we go to helium, the alpha particle, helium-4, now we have 2 protons in the 1s 1/2, which we go by putting a square there. And the 2 there represents the occupancy of that shell, and that's a closed shell for protons. We also have a closed shell for neutrons that we indicate in the same way. And now we have a doubly closed shell for both protons and neutrons. We can continue in this way for, say, if we want to have oxygen 17. So oxygen 17 has a complete 1s closed shell. The next level up is the p 3/2 state. So n equals 1, p, so L equals 1, but the spin and the spin 1/2 and the L equals 1 are aligned, so we get a J equals 3/2 total state. There are 3/2. 3/2 has a multiplicity of 4, 3/2. So we go from minus 3/2 to plus 3/2 in steps of 1. So minus 3/2, minus 1/2, 1/2, 3/2, 4 of them, but they're all filled. And then we have the 1p 1/2 state where the spin is anti-aligned. So it's p L equals 1, S is 1, but it subtracts, so we have a total spin of 1/2. There's 2 of those, and they're both filled. For oxygen 17, there are 8 protons. The neutrons go through the same states, 1p 3/2, of which there are 4, 1p 1/2, of which there are 2, and then there is one lone remaining neutron, which has to go in the next shell. So as we go up here, we go through 1s, 1p 3/2, 1p 5/2. The next state is a 1d 5/2 state. And so here we say that there's a 1d 5/2 state. There's 1 there, and that one remaining neutron, unpaired in the high shell, determines most of the properties of oxygen 17. Usually one can ignore all this part and just look at this last bit, the unpaired electron, or sorry, unpaired neutron or unpaired proton, to determine what happens in a nucleus. So for instance, in 25 magnesium, which has 12, we can ignore the completed shells, which is the oxygen 16 states, the 1s squared, 2p3 halves to the fourth, 1p3 half, 1 half squared, and just write down that there are, for the protons, there are 4 protons in the 1d5 halves state, and likewise the neutrons, there are 5 of them in that state. That means there'll be 1 unpaired neutron in this state, and that will determine most of the properties.